No, you're good. It's back there. Okay, so this whole question is about KSP and solubility. I want to make you aware that this question is from 2004, and the test changed significantly in 2014. So originally they would have questions like this that were very focused on one topic. And teachers complained because if a student gets to this question on an AP test, and that's the one thing that they're not good at, they've just lost 10 points. And teachers didn't really think that was fair. When we're teaching you so much material, and then they're focusing on one little thing, that's unfair. So now you'll see KSP show up maybe 1 or 2 times on the test for 1 or 2 points, but it will never be 10 whole entire points like this. Because this just annihilated students' scores who maybe that was the one topic they were confused on, or the one topic they missed, or whatever. But anyway, we're going to go through this. So write the equilibrium constant expression for the dissolving of silver chromate. So KSP equals the concentration of silver squared times the concentration of chromate. Questions about that? We don't include solids, so the reactant wasn't included. Calculate the concentration in moles per liter of silver in a saturated solution of silver chromate. So here's the thing. Silver is 2 times chromate. So silver is 2x. So if we wrote this in terms of x, it would be KSP equals 2x squared times x, right? It's a 1 to 2 ratio. So KSP equals 4x cubed. They gave me KSP 2.6 times 10 to the negative 12th. Divide by 4, take the cube root. Once you have x, I don't know what it is, but it doesn't matter, then you just take 2 times that to find silver. So the concentration of silver is 2x. Questions? All right. C, calculate the maximum mass in grams of silver chromate that can dissolve in 100 milliliters of water. So X, question mark, is the moles per liter. That's the molarity of chromate and the moles per liter of this that dissolve. So 0.1 liters, the molarity, so question mark moles over 1 liter, and then 1 mole is the molar mass of silver chromate. Anybody have that? 3 something? 331. Multiply across the top times question mark, whatever that was, and that will give you your grams. And then the last part of this one, a 0.1 whole solid sample of solid silver nitrate is added. Assuming no volume change, does the chromate increase, decrease, or remain the same? So we're adding silver nitrate, which means we're adding silver, right? If I add stuff to this side, it's going to shift to the left. K, Q, all that stuff. If it shifts to the left, my chromate will decrease. That's that Le Chatelier's principle thing. You put some of this in, it's going to shift this way. If it shifts this way, I have less of this. Yes? All right. The next one is silver phosphate write the balanced equation for the dissolving of silver phosphate. Looks like that. Has to be equilibrium because it's dissolving.
So it is like both ways?
Yep. Calculate the value of KSP for silver phosphate. So they give me silver, and I need phosphate. So KSP equals silver cubed times phosphate. They gave me silver as 5.3 times 10 to the negative fifth. Yeah. So phosphate, because it's a 1-to-3 ratio, is a third of that. And then I just plug those two numbers in here and get a really small number. Something times 10 to the negative 12, I think. Maybe bigger than that? Smaller than that?
Not smaller.
Okay, I don't know. And then the last one, a 1 liter sample of silver phosphate solution is allowed to evaporate at 25 degrees Celsius to a final volume of 50 milliliters. What is the silver concentration in the solution? That doesn't matter. If it's evaporating, the concentration is not changing. That's constant. Questions? Comments? Concerns? No? All right, take out your notes so we can start Unit 9. Okay, so Unit 9 really covers two topics. It goes more in depth on thermodynamics. We already talked a little bit about thermodynamics when we talked about specific heat, like Q, and when we talked about enthalpy. Remember, enthalpy is the whole endothermic, exothermic thing, change in energy. And then it goes into electrochemistry. Electrochemistry is like galvanic cells, batteries that are made from chemical reactions. If you've had physics, this will kind of be review. We're going to start with the thermo part, and then we'll get into electrochem. So, enthalpy, remember, is energy, the change in energy, joules per mole. This starts with entropy. And the best definition I can give you for entropy, which is a very abstract concept, is the disorder of a system. And when you think of disorder, you need to focus on the particles in the thing. So, we're going to compare things a lot of times when we're talking about entropy. So think about the hallway. If you went out in the hallway right now and walked to the attendance office, there would be very little chaos in that path, right? You wouldn't see a lot of people. You could walk pretty straight there and pretty straight back and maybe not see anybody besides the people in attendance. That's low disorder. That's low entropy. Opposite, if I tried to send you to the attendance office in the middle of passing period, you would encounter a lot of people. There would be a lot of chaos. That's high entropy, high disorder. So when we're talking about chemical systems and their entropy, usually we're going to be comparing things like that. A solid compared to a liquid. A gas at a high temperature compared to a gas at a lower temperature. Some things have more entropy than others. The universe favors low entropy. The universe itself is trying to decrease the entropy, right? But we know that ever since the dawn of time, entropy is constantly increasing, right? We're constantly creating more disorder because things are constantly reacting, things are constantly things are happening to increase entropy. But reactions themselves try to minimize it, and we'll talk way more about that as we go. All right. By definition, the only thing in the universe that has zero entropy is a perfect crystal at 0 Kelvin. And entropy is S. S equals 0. Because E is energy, H is enthalpy, S is entropy. I don't know why. But S equals 0 for a perfect crystal at 0 Kelvin. So again, this is very theoretical. It's not something that has ever happened because we've never gotten anything to 0 Kelvin. But they're trying to give this some type of meaning. So if entropy is disorder, the thing in the universe with the least amount of disorder, or the most ordered thing, would be a perfect crystal. I'm talking about like diamond. If you look at diamond under a very strong electron microscope, the carbon atoms are in a perfect pattern. A very rigid, perfect pattern. Crystal structure. And if you make it at 0 Kelvin, are those carbon atoms moving? Not at all. There is absolutely no disorder in the system. It doesn't exist. But that's kind of how we're trying to define entropy. So everything else, which is everything, has some amount of entropy. A diamond at 5 Kelvin doesn't have very much entropy at all. Hydrogen at 5,000 Kelvin has tons of disorder, tons of entropy. You kind of see how this all relates? Entropy, I know, is very abstract. It's not something that we can necessarily measure. It's more of a comparison thing. This has more than this. In this reaction, entropy increased. In this reaction, entropy decreased. But to actually find numbers, you just have to look those up in books. Okay? Yep.
Can you normally tell if entropy increases or decreases just based on the temperature?
On the temperature, or if the temperature is staying constant, if phases are changing, or if the phases aren't changing, if you're increasing number of moles or things like that. But it's something along those lines. Okay. So, here are some examples of what we were just talking about. The entropy of solids is less than the entropy of liquids, and those are both much, much less than the entropy of gases. Order, less order, disorder. Make sense? Gases are chaotic. They're moving fast, they're moving randomly, all those things. The entropy of a small number of particles is less than the entropy of a large number of particles. That's our hallway example. Less stuff is easier to keep in order. Right? The entropy of gases with smaller volumes is less than the entropy of gases with larger volumes. You give things more space, there's going to be more chaos. Right? As a teacher, I think of, if I'm going to go on a field trip, I would not want to take my students to a field trip in a forest. That's too much space for you all to disperse. That's a lot of chaos. I'd rather take you on a field trip to a museum where I can keep you contained. Does that make sense? Disorder. Entropy increases with increasing temperature. Kinetic molecular theory says those particles are moving faster. Faster particles, more disorder. Are you kind of starting to grasp this idea of entropy? It's abstract. I remember the first time I learned it thinking, what? Why? Well, you'll see why soon. Okay. So now, if we're talking about S, we can measure delta S, the change in entropy in a reaction, right? So delta S is equal to the S of the reactants, products, minus the S of the reactants. You'll often see it like this with this knot here. That means at STP, standard conditions. Okay, so for this reaction, I have a solid and a liquid reacting to create just a solid. Is entropy increasing or decreasing? What? Solid and liquid going to just a solid. It's decreasing. So my delta S is negative. My products have less entropy than my reactants. Less order, more order. Okay? Solid sodium carbonate going to sodium oxide and carbon dioxide gas. Increasing or decreasing? It's increasing, right? There's more disorder in a gas. Yep.
Is there like a property, I guess, that's more important when talking about entropy, like the state versus number of particles?
Yes, but not in this class. In this class, it will always be like everything else is the same, except we're changing one thing. They won't expect you to choose like temperature over phase or metal over non-metal. Like nothing. They'll always be the same except for one thing. And here. So a metal at 273 Kelvin or the same metal at 400 Kelvin, which has more entropy? The 400 Kelvin metal. Higher temperature, more entropy. A flexible soft metal like lead or diamond, a rigid solid, which has more entropy? The what? The soft metal. More movement, more entropy. Two samples of the same gas at the same temperature, but one at 1 atmosphere and the other at 0.5 atmospheres. Which one will have more entropy? The 0.5. Less pressure, more movement, more entropy. Are we good so far? Okay. All of this that we know so far, enthalpy and entropy, come together into something called Gibbs free energy. Gibbs free energy is the combination of enthalpy and entropy that's happening in a reaction. Because both things take place. Both things are important. Enthalpy, meaning is the reaction endothermic or exothermic? Right? That's what enthalpy tells us. Does it require energy or does it release energy? And now this also includes entropy. Is entropy increasing or decreasing? It's the combination of those things at a given temperature that determines if a reaction is what we call thermodynamically, which is a very long word, favorable or unfavorable. And all this means is if I take my reactants and combine them at that temperature, will it go or not go? React or not? We know that you can mix two things together at some temperature and they never react ever. They just sit there for all of eternity. That is a thermodynamically unfavorable reaction. But then if I took it and put it on a hot plate, it might go because I increased the temperature. This is all temperature dependent. Okay, if it is thermodynamically favored, delta G is negative. If it is unfavorable, delta G is positive. And the way I find this is called the Gibbs free energy equation or Gibbs-Helmholtz equation. The free energy of a reaction is equal to the enthalpy, endothermic or exothermic, minus the temperature in Kelvin times the entropy. So far, so good? Okay, let's look at this table. All right, so remember, enthalpy, delta H. Positive means endothermic, negative means exothermic. Energy required, energy released. Entropy, positive means increased disorder, negative means decreased disorder. And then we're looking at this equation. So, if delta H is positive and delta S is positive, this is negative at high temperatures. If T is a big number, you'll have a favorable reaction. That's what I was just talking about. Some reactions only go at high temperatures. At low temperatures, it won't go anywhere because it requires energy and it increases entropy. An endothermic reaction that decreases entropy will never go anywhere. It's always positive. Those reactions just don't happen. You can't require energy and decrease entropy at any temperature. The universe does not allow it. An exothermic reaction that increases entropy is always allowed. It will always happen. Doesn't require energy, increases entropy, that's good, according to the universe. An exothermic reaction that decreases entropy will happen at low temperatures, will not happen at high temperatures. Those are weird. We don't encounter those as often. These are reactions that require cold temperatures. You have to put it on ice for it to go. It's not often, but it happens.
What's an example of that?
Do you remember? Well, no, because we didn't get to do it because of COVID. There's a reaction where you're forming copper oxide, and it would happen over time, but it happens faster at low temperatures. There aren't a lot of them. And I'm sure there are others that I don't know because my brain isn't an encyclopedia, but for our purposes, not very many. Questions about this? You don't have homework. Your only job is to read these pages and really try to grasp these concepts of entropy, enthalpy, Gibbs free energy, and how they all relate. Lovely. That's it.